In the second quarter of 2021, Polygon had more daily active users than Ethereum. And beside Polygon, there are many other scaling solutions for Ethereum. And as a developer, you have to know about them, but there are so many projects and it's easy to get lost. In this video, I will introduce the top 3 scaling solutions for Ethereum that you absolutely have to know. If you don't know me, I'm Julien, and on EatTheBlocks, I teach blockchain development. Every time the Ethereum blockchain becomes really popular, the network becomes sluggish and the transaction fees becomes very high. This happened when CryptoKitties was launched in 2018, this happened during the DeFi summer of 2020, and this happened again in the DeFi bull run of 2021. That's why the Ethereum community is working on making Ethereum more scalable. One way to make Ethereum more scalable is with on-chain scaling. With on-chain scaling, we work directly on the Ethereum protocol itself. The problem with on-chain scaling is that we have to make trade-offs. Out of decentralization, security, and scalability, we can only have 2 of them. For example, if we increase the block size, more transactions can fit inside, which makes the blockchain more scalable, but we also make it harder for miners to mine new blocks, which requires better hardware than few miners can afford, which reduces decentralization. Ethereum 2.0 is going to make Ethereum scalable without significant trade-offs, but this is a hard problem to solve, and we still need to wait a few years before it's ready. That's why we need other scaling approaches that will be available faster. And for that, we have off-chain scaling solutions. With off-chain scaling, we make Ethereum scalable by building on top of Ethereum, but without changing the Ethereum protocol itself. There are many approaches for off-chain scaling. Some of them rely on Ethereum for their security. We call them layer 2. Some others rely mostly on their own consensus algorithm for security. We call them sidechains. And some are hybrids. The first off-chain scaling solution that I will introduce is channels. There are 2 kinds of channels, state and payment channels. Payment channels are for scaling payments, and state channels are for scaling any arbitrary smart contract execution. I'm going to explain how a payment channel works because it's most simple, but for a state channel it's very similar. In a payment channel, Bob and Alice wants to make a series of payments between themselves. Bob and Alice will first lock an initial balance of Ether in a multi-sig smart contract on Ethereum. After, Bob and Alice will send some payments to each other by sending messages with their private key. For example, if Bob renders a service to Alice that costs 1 Ether to Alice, Bob will send a message with the updated balance of each participant of the channel, which means there will be 1 more Ether for him and 1 less Ether for Alice. If Alice agrees, she signs the message. They keep the channel open as long as they want, signing new messages every time there is a new transaction. At any time, they can decide to close the channel by submitting the final state to the multi-sig smart contract on Ethereum. This smart contract verifies that the final state was signed by both parties. Then it will wait during a duration that we call the challenge period to see if any parties challenge the final state by submitting a more recent state also signed by both parties. After the challenge period is over, if no party has challenged the final state, both participants are able to withdraw their money according to the balances of the final state. In terms of pros, it allows instant withdrawals. It also allows an extremely high throughput. Because all the transactions in the channels only need to be processed by the participant of the channel and not by all the nodes of the network. And it also has a very low cost per transaction, which is good for streaming micropayments. In terms of cons, it can be quite costly to settle a channel because we have to deploy new smart contract for each channel, and especially for state channel, the multi-sig smart contract needs to know the application logic, so this is application specific. In order to ensure the security of your funds, you also need to periodically watch the network and challenge the final state of the multi-sig smart contract if you ever spot a fraud. That's what we call the liveliness requirements. You also have to lock up funds to open the channels, and it doesn't support open participation, which means we need to know all the participants at the beginning of the channel. Channels were a good first attempt to scale blockchain, but they are also quite limited, and in the meantime we had more modern approaches. A sidechain is a separate blockchain which runs in parallel to Ethereum mainnet and operates independently. It has its own consensus algorithm like proof of authority, delegated proof of stake, etc. It's connected to mainnet by a two-way bridge, which allow you to transfer assets back and forth. What makes a sidechain really exciting is that the chain works the same way as the main Ethereum chain because it's based on the EVM. This means that if you want to use your dApp on a sidechain, it's just a matter of deploying your code to this sidechain, and it looks, feels, and acts just like mainnet. You write your smart contract in Solidity, and you interact with the chain using the Web3 API. So in terms of pros, sidechains are an established technology, and it supports general computation of smart contract with EVM compatibility. In terms of cons, this is less decentralized than Ethereum. It also uses a separate consensus mechanism, which is not secure by layer 1. And there is a possibility that there will be a quorum of sidechain validators that commit fraud, and it's much easier to reach this quorum on a sidechain than on Ethereum L1. So sidechains are a good practical solution to the problem of scalability, but because of the lack of decentralization, it cannot be the ultimate solution for scaling Ethereum. Next, we have plasma chains. A plasma chain is a separate chain with its own consensus algorithm. This part is similar to sidechains. However, contrary to sidechains, plasma chain post the root hash of each of their blocks to Ethereum L1. This can be used to submit fraud proof to Ethereum L1 when someone spots a wrong transaction on the plasma chain. So you can say that the plasma chain is a child chain of Ethereum that is anchored to Ethereum L1. In terms of pros, a plasma chain offers a high throughput and a low cost per transaction. It's also good for transactions between arbitrary users. If the users are already established in the plasma chain, they can interact with each other. In terms of cons, it doesn't support general computation, only basic token transfers, swaps, and a few other transaction types that are supported by a logic already pre-established. We also have the liveliness requirement, which means each user or a delegate needs to continually watch the network and potentially submit fraud proof if we spot any wrong transaction. That's how we guarantee the security of the plasma chain. It also relies on one or more operators to store data and serve it upon request, but some operators can decide to withhold data. And finally, when you want to withdraw from the plasma chain to Ethereum L1, you have to wait for the challenge period, which can last up to 1 week. Plasma was originally thought to be the solution to off-chain scaling, but it became soon apparent that it posed some practical problems that couldn't be solved. There is the problem of the challenge period that I just mentioned. Another problem is the liveliness requirement, which means each user has to monitor and verify that his transactions are correct. Most users cannot do that, and it's not easy to delegate this task. And there is also the problem of the mass exit. If an operator of the plasma chain decides to not publish transaction data, each user needs to individually exit the chain based on the last valid state, and it would create a huge bottleneck of incoming data to Ethereum, which would clog the network and prevent users from exiting. So because of this, Ethereum researchers kept working on other solutions and created something new called rollups. Plasma and channels are full layer 2 scaling solutions because they move transaction and computation data off-chain. Rollups are hybrid layer 2 scaling solutions because they move computation and state storage off-chain but keep some data per transaction on-chain. There are two flavors of rollups: optimistic rollups and zero knowledge rollups. Let's start with optimistic rollups. In a rollup chain, we have a rollup smart contract and sequencers. The first step is when a user deposits some ether or tokens in a rollup chain. For this, the user sends some crypto to the rollup smart contract on Ethereum L1. After, the user can do some transaction on the rollup chain. When a user creates a transaction on a rollup chain, his wallet sends a transaction to what is called a sequencer. That's the equivalent of a miner. Anybody can be a sequencer. The sequencer will execute the transaction as well as other people's transaction in what we call a batch. After that, he will update the state of the rollup chain. This means updating ether balances, ERC20 balances, storing code of your smart contract deployed, etc. But all of this happens outside of Ethereum L1. After, the sequencer will send a single transaction to the rollup smart contract on Ethereum L1. This transaction will contain all the rollup transactions of the batch, the pre-state route, and the post-state route. The rollup transactions are not stored in the blockchain storage of Ethereum L1. They are just part of what we call call data, or in other words, the arguments of a function call in a transaction. Call data is cheaper than EVM storage, but it cannot be read or modified by the EVM. It can only be read by outside clients. This is required for ensuring the security of the rollup. Technically, the state root is a Merkleized hash of the state of the rollup, or in more simple terms, this is a digital fingerprint representing the state of the rollup chain. The pre-state root represents the state of the rollup chain before all transactions are applied. The post-state root is the hash of the updated state of the rollup after the transactions of the latest batch are applied. The updated state root is stored in the EVM storage that's different from the transaction data. At this point, the rollup smart contract doesn't make any verification. It just assumes that the new state root is valid. And from the sequencer point of view, it represents a commitment that if we apply all these transactions, it will result in the state that was posted. After, anybody can observe the rollup data that was posted by the sequencer. If anybody finds an error, he or she can challenge the sequencer in a certain time period. For this, you need to submit a fraud proof to the rollup smart contract. Using the transaction data that is published by each sequencer, it's possible for anybody to replay all transactions and prove that there was an error. The rollup smart contract is able to check the validity of a fraud proof, and if it finds that the fraud proof is valid, it will revert the rollup chain to the latest correct state, penalize the bad sequencer by slashing its bond, and that's because each sequencer has to post a bond before being able to post transaction batch. This way, sequencers have an incentive to be honest. So in terms of pros, anything you can do on Ethereum layer 1, you can also do on Optimistic rollup because it's EVM and Solidity compatible. And it's also secure and decentralized because all transaction data is stored on the layer 1 chain. And this way we also avoid the data availability problem of Plasma. In terms of cons, unfortunately, when you want to withdraw your crypto from the rollup chain to Ethereum L1, there are long wait times to allow for potential fraud challenges. And finally, sequencers can influence transaction ordering. Next, we are going to talk about the other flavor of rollup, zero-knowledge rollups. The big difference compared to optimistic rollups is that with zero-knowledge rollup, when a sequencer posts transaction data to Ethereum L1, we are sure that the updated state is valid. We have finality on the transaction right away. There is no need for a challenge period after. And that's because the sequencer posts a validity proof that can be verified by the rollup smart contract on Ethereum. This validity proof is created by the sequencer using a mathematical technique called zero-knowledge proofs. With a zero-knowledge proof, a prover can prove that he knows some information without revealing the information itself. In terms of pros, the bigger advantage is that it offers a faster finality, since the state can be instantly verified once the proofs are sent to the main chain, and it's also secure and decentralized since the data that is needed to recover the state is stored on the layer 1 chain. In terms of cons, some implementation don't support EVM yet, validity proofs are intense to create, and it's not worth it for applications with little on-chain activity. And finally, sequencers can influence transaction ordering. So out of all these scaling solutions, which one is the best? For this, I will quote Vitalik Buterin, the creator of Ethereum. In general, my own view is that in the short term, optimistic rollups are likely to win out for general purpose EVM computation, and zero-knowledge rollups are likely to win out for simple payments, exchange, and other application-specific use cases. But in the medium to long term, zero-knowledge rollup will win out in all cases as zero-knowledge snark technology improves. What's also interesting to note is that Vitalik Buterin is in favor of making some small changes to Ethereum L1 to help for the implementation of rollups. So that's it for the high-level overview of the different scaling solutions. Next, we're going to dive in specific implementations. Polygon, formerly known as Matic, is the most popular scaling solution for Ethereum. The native token of Polygon has a market cap of $8.6 billion and is ranked number 18 on CoinMarketCap. If we only consider Ethereum scaling solutions, that's the first market cap. According to a report of DappRadar, Polygon has caught up with Ethereum in terms of daily active user and even surpassed it for a short moment. That's really impressive considering that Polygon is a very recent project. On cryptofees.info, we can see a list of blockchain and DeFi projects ranked according to the transaction fees they generated. And you can see that QuickSwap, a project of Polygon, is pretty high up in the list, not too far from Bitcoin and Compound. And for transaction fees collected by the Polygon network itself, it's about $30 million per day. On awesomepolygon.com, you will find a list of projects deployed on Polygon, and there are more than 500 projects listed. Most of them are either DeFi or NFT projects. For example, QuickSwap is a decentralized exchange, Aave is a decentralized lending platform, and Aave Gochi is an NFT game. Some of these projects are native to Polygon, like QuickSwap. Some were originally deployed to Ethereum and later deployed a second time to Polygon, like Aave. And some were originally deployed to Ethereum and migrated later to Polygon, like Aave Gochi. On that radar, you can see another list of projects deployed on Polygon with some transaction and usage metrics. The biggest dApp of Polygon is QuickSwap, and in the last 30 days, it had more than 200,000 users and $4 billion of transaction volume. Polygon received several rounds of funding, but the latest rounds have undisclosed amounts. There were probably big amounts because Polygon launched a fund of $100 million to support DeFi projects that are launching on Polygon. This means that as a builder, you can get funding for DeFi project if you decide to deploy it on Polygon. Next, let's dive into the technical details. Polygon has a block time of 2.4 seconds, much faster than the 15 seconds of Ethereum. On the testnet, it has reached 7,200 transactions per second, which is much higher than the 10-15 transactions per second of Ethereum. And transaction fees are also much lower, up to 100 times less. Polygon is a sidechain, meaning that it has its own consensus algorithm independent from Ethereum. It also has some elements of the Plasma framework. It is connected to Ethereum in two ways. First, the state of Polygon is regularly checkpointed on Ethereum L1, meaning that we store hashes of the state of Polygon in Ethereum every 5 minutes. This can be used to verify the validity of transactions on Polygon. Second, anybody can challenge the validity of a transaction on Polygon by submitting a fraud proof to a smart contract on Ethereum. The entity that validate block on Polygon are called validators. These validators stake some Polygon tokens on Ethereum. If someone can prove that a transaction is wrong, the stake of the validator will be slashed. So validators have an incentive to not be dishonest. For users, using a dApp on Polygon is very similar to using a dApp on Ethereum. Users just have to configure a new network in MetaMask and they are ready for Polygon dApps. Where it gets a bit tricky is for transfer of assets between Ethereum and Polygon. From Ethereum to Polygon, it's fast, but from Polygon to Ethereum, you have to wait 7 days. For developers, developing on Polygon is almost the same as on Ethereum. Polygon is an EVM blockchain, which means you can use all the development tools of Ethereum. You write your smart contract with Solidity, you can use frameworks like Truffle, Hat or OpenZeppelin, and you can use ERC20 or ERC721 tokens. Polygon has some public RPC endpoints, but I found them a bit unreliable sometimes, and you can also use endpoints for Polygon on the free plan of Infura. What I just described is only the POS chain of Polygon. They are also working on an implementation of optimistic rollup and zero knowledge rollup, but we will have to wait until it's ready to be used. And they are also working on supporting base chains other than Ethereum. So that's it for Polygon. Next, we are going to continue with another important project for scaling Ethereum. Optimism is one of the most promising projects for layer 2 scaling on Ethereum. Contrary to Polygon, Optimism doesn't have a native token, so you won't find this project on CoinMarketCap. On cryptofees.info, we can see that Optimism is ranked 13 over 37 for the top project that collect the most fees in blockchain. It's a top layer 2 project even before Polygon. And what's really impressive is that they already have all this activity even though they are not fully live. They currently have a permission mainnet deployment, which means only whitelisted projects can sign up. They do this to be as cautious as possible and make sure that when they finally open the mainnet to everybody, everything works fine. Normally the public mainnet should be open for this summer, but it was already delayed a couple of times, so it seems like we have to wait a bit. For the projects that are already live on the permission mainnet, there are already a few big names in DeFi like Uniswap and Synthetix. In terms of technology, Optimism uses optimistic rollup. One of the main challenges of optimistic rollup is to have compatibility with the EVM, or in other words, to be able to run any arbitrary smart contracts. Optimism is the first project that created an EVM compatible implementation for optimistic rollups. That means you can use all the development tools of Ethereum and it works great. Even though the public testnet is not ready yet, you can already deploy to that testnet. I already deployed a smart contract to the testnet, and with my knowledge of Ethereum, it was really smooth. The only caveat is that they use a slightly different version of Solidity. That's because of some obscure technical detail about optimistic rollups, and there are also a few restrictions about smart contracts on Ethereum. So when you develop on Optimism, remember about this custom version of Solidity, and you can find more details on the truffle box for Optimism. To deploy to Optimism, you need an Optimism node, but fortunately they have a public endpoint and Infra provides one as well. Okay, so that's it for Optimism. Next, we're going to continue with another interesting project for layer 2 on Ethereum. Arbitrum is another very promising project for layer 2 scaling on Ethereum. Like Optimism, it doesn't have a native token. Like Optimism again, they currently have a permission mainnet deployment, which means projects need to sign up. They call their mainnet deployment Arbitrum 1. They have more than 250 projects which sign up, including some big names like Uniswap, SushiSwap, and Chainlink. Another big partner is Reddit. Reddit announced they will use Arbitrum for their community points. This is really great because Reddit has a ton of users and community points will probably be a very popular feature. And soon Arbitrum will open up to any project without requiring to sign up. In terms of technology, Arbitrum, like Optimism, uses optimistic rollup. And it also supports the EVM, which means you can use all the development tools of Ethereum. Like for Optimism, Arbitrum has public endpoints and Infra provides an endpoint as well, which makes deployment easy. A big difference with Optimism is that on Arbitrum, you don't need to use a different version of Solidity to write your smart contract. Small details to note, even though you don't need to use a different Solidity compiler, there are some small differences in constants and built-in function. You can find the details in their documentation. Another big difference between Optimism and Arbitrum is how they handle fraud proofs. Arbitrum fraud proofs try to find the particular point of disagreement in transaction history. The technical terms is multi-run fraud proof. Optimism looks at frauds in a more global way using a technical single-run fraud proofs. Without getting into the details, it means Arbitrum has a higher transaction capacity. Another difference is that Optimism uses wrap Ether while Arbitrum has native Ethereum support. And a last difference with Optimism is that the Arbitrum node allows not only to run optimistic rollup but also sidechains and channels. Gives you more flexibility to experiment with other scaling techniques. Now you know the top 3 scaling solutions for Ethereum. If you build a dApp, should you even bother to deploy your dApp there, or can you just deploy to Ethereum L1? If your dApp has high value transactions where security is extremely important and your users don't mind to pay high transaction fees, you can just deploy your dApp on Ethereum L1. That's the case of some whales on some decentralized exchanges, for example. For most dApp, users will be willing to trade some security against cheaper transaction fees, and they don't even have to give up a lot of security. These scaling solutions are in general quite secure, even though they are not as secure as Ethereum L1. If you decide to use a scaling solution for your dApp, which one should you choose? At the time of releasing this video, the answer is Polygon. Polygon is the only scaling solution that is ready for production. They have the biggest dApp activity, the tooling is quite mature, and if you launch a DeFi dApp, you can receive some funding by applying to their $100 million fund. In terms of scaling technology, the most promising solution is zero-knowledge rollups because it doesn't have any residual time. There aren't many projects in production today for zero-knowledge rollup, but you can follow a project called ZK Sync because it's making big progress. If you want to start experimenting with Polygon and other scaling solutions, you can check out this tutorial where we deploy a smart contract to Polygon and Optimism. I'll see you there.